Okay, we were discussing how Hadamard gate operates on state 1, and we saw that Hadamard gate takes state 1 to a combination of 0 and 1, but then it is now 0 minus 1 by root 2, unlike when it is applied to 0 when it is 0 plus 1 over root 2. Okay, so uh, this negative sign that comes, this negative sign is nothing but a phase. Uh, Technically, we call this, just a second. So here pi is the phase and e to the power I pi is the phase factor actually. So just for the sake of completion, I will write this as phase factor, uh, and pi equals to the pi is the phase angle. Uh, so just for the sake of completion, this is some extra information. Whenever we have this e power I theta, we this value, whatever value results, can be considered as a phase factor, where theta is the phase or phase angle, or yeah, usually people say it as the phase. And e power I theta uh, uh, is nothing but cos theta plus I times sine theta. So for different values of theta, we get different results. For example, when theta equals to pi, we get e power I theta equals to cos pi plus I times sine pi. Uh, so sine pi is 0, and uh, cos pi then becomes minus 1, right? And that's why it's minus 1. Similarly, for theta equals to pi over 2, we get e power I theta equals to cos pi by 2 plus I times sine pi by 2. And now cos pi over 2 is 0. So, and sine pi over 2 equals to 1. That's why I'm left with just I. Oops. I'm left with I. And one last angle could be uh, theta equals to pi by 4. And this would result in e pi theta equals to cos pi over 4 plus I sine pi over 4. And we know cos pi over 4 is 1 by root 2 as well as sine pi by 4. So this becomes 1 by root 2 times 1 plus I. Okay. So these are the three different phase angles, and we'll see that we have three different gates based on these three different phase angles. One we uh, uh, no, we haven't seen any, but I'll show you in a moment. Anyway, so coming back to the problem, Hadamard gate when applies to state 1, it gives me a phase factor of minus 1 in front of state 1, and we get a 0 minus 1 over root 2. So let's get back to our composer, IBM Quantum Composer, and see what happens when we apply Hadamard gate to state 1. But then all the states are initialized at 0, right? And we have already seen that when it's applied to 0 state, we get a 50-50 probability distribution of 0 and 1. And here also, this blue color, so there's this state and there is this state, so it's a superposition of this state, the output. And this blue color refers to, you can see that blue refers to phase 0. We can also see the phase angle. So phase angle is here, this value, which is 0. Now we want to apply Hadamard gate to state 1. but then all the qubits are initialized in state 0 only. So we need to first make this state 1, and then only we apply Hadamard gate. This is where we should have a look at X gate. I'm sure you would be knowing about it already. So the action of X gate is it makes 0, 1, and it makes uh, 1, 0. So it acts as a bit flip gate because it's making it's changing 1 to 0 and 0 to 1. So X gate is also called as bit flip gate. It's flipping the bit, right? Bit flip gate. And if I would apply X to a general qubit, let's say something alpha 0 plus beta 1, a general qubit state, then it would act like alpha, and then X would operate on 0 plus beta, and then X would operate on 1. So it would give me uh, alpha times 1 plus beta times 0. In other words, uh, I can write that alpha beta state upon the action of X becomes beta alpha. All right. Let's verify it. So for the moment, I'll just delete it and apply X gate. So now we can see that the state is initialized in 0, and this is the X gate here. We see that the state changes to 1. Similarly, if I apply X gate on state 1, so now it is state 1, right? It will change to 0 back. We can also see here that X applied twice is basically doing nothing, right? So I can also say that X square equals to identity. And I'm not sure if I mentioned it already, but one can also notice that just a moment. Yeah. So I was saying that X square equals to identity. This, and one can also notice that even Hadamard has the same property. So if we apply Hadamard gate twice, then also it is it undo when you apply the Hadamard for the second time, it undo the effect of the first Hadamard. So I can show it this way. Let's apply 2 Hadamards. I apply first Hadamard, it creates a superposition, and then I applied another Hadamard, and it destroys the superposition. Basically, it is doing nothing if you apply 2 Hadamards. So H square equals to 1. Okay. Now we wanted to see what happens when Hadamard applies to state 1. So to create state 1, I apply X gate to state 0. And we see that the state has changed to 1, right? Now I'll apply Hadamard to it, and we'll know that we'll get a superposition of 0 and 1. But then here you see that now we get a red line here. So this is the phase pi. So now when we apply Hadamard gate to state 1, we get a superposition of 0 and -1 state. If we apply Hadamard to state 0, we get a superposition of 0 and +1 state. Okay. That's good. So we learned about Hadamard gate and X gate. Now let's look at another important gate, Z gate. So next we'll look at Z gate. Some people also prefer calling it phase gate for the reason we'll see now. Here I'll just mention X gate. So the way Z gate acts on states is the following. does nothing to state 0, but it changes state 1. It changes state 1 to -1. Uh, yeah, so I can also say that when Z gate is applied to 1, it introduces a phase of -1, right? Or an phase angle of pi. So this is nothing but e to the power I pi times 1. Um, so I can also say that uh, Z gate introduced when in e power I theta. If theta equals to pi, then it becomes -1, right? So Z gate, I can write something like Z gate as a function of theta and x on state 1 is e power I theta 1 with theta equals to pi. Right? The reason I have written it is the following. There are also some other gates which introduces uh, a, a phase of a few different angles, but only to state 1, right? So we'll get to that a little later, but for the time being, I'll just show you that Z gate does nothing to state 0, but it changes the sign of state 1 to -1. Okay, so we have the state 0 in Q0. Let's apply a Z gate. So it does nothing, right? Nothing changed. Probability distribution stayed the same, and also, on the qubit pair, things stayed the same. Now, if I apply Z gate to state 1, so to do that, I'll apply a X gate to state 0 first. And that I can do by just dragging it, and I can always hover over things here. So I could take it right, left, and then I'll just sandwich it here. This means that first this is applied and then this. So this is something to note. In this circuit, it goes from left to right, right? So when I apply this X gate first, it is the X gate that is applied first, and then the Z gate. So once X gate is applied to 0, I get a state 1, and then the Z gate is applied. We see the probability distribution stayed the same. I mean, it just changed the state 1. So what I'm trying to say, if we just apply the X gate, it's in state 1 right now, because X changes state 0 to 1. And after that, if we apply gate Z, it still stays the same. But the difference comes here. Now we see they develop a phase angle of pi here, right? And at the change also color. The color also changed to red. So this brought a phase difference of pi. And if I delete this, if I delete Z, then it comes back to no phase. Also, if I keep the Z gate twice, it also cancels the effect, right? Because now Z and Z, it applies a phase of 2 pi. So first Z applies a phase of pi, and the second Z applies a phase of pi. So both of them apply a phase of 2 pi together, and 2 pi phase is basically coming back to the same place in the coordinate space, right? So we can also say that Z square is equals to 1. So you can say that Z square is also equals to identity. All right. So that's about Z gate. What are the other gates which also add phase in terms of e power I theta? They are S and T gates. But before getting into S and T gates, I would just like to give uh, some little more information, and that is the matrix structure of quantum gates. So matrix structure of quantum gates. So what I'm trying to tell is this X gate should be a 2 cross 2 matrix because this 0 is a vector, right? 1 0, and 1 is also a vector, 0 1. So if a operator is operated on this state, which is a 2 cross 1 vector, which are 2 cross 1 vectors, then the operator must be a matrix of 2 cross 2 order. So X gate takes 0 to 1 and 1 to 0. That means uh, this matrix, when applied to when applied to 1 0, then it gives me a 0 1. And a quick inspection can give us the result that for this to happen, the matrix must be 1 1 0 0. Also, to give us a state of 1 0 from 0 1, so that is taking state. So here it took state 0 to state 1, right? Here it is taking state 1 to state 0. The same matrix will work. Okay. So 0 applied to 0 is 0, and 1 applied to 1 is, sorry, 1. 0 into 0 is 0, and 1 into 1. So you could do this matrix multiplication. It's easy. My point is, because of this, the structure of X matrix is the following. It is a 2 cross 2 matrix with this value. And you can check that X square is going to be 1 as well. Yeah, so this is the matrix structure. We can also note that this matrix structure is also, I mean, there's an intuitive way of looking at it. So this column is the output when X will operate on state 0. Output when it operates on 0. And this column is the output when it operates on state 1. So what I'm trying to tell here is, for a general single qubit gate, so here we are operating gates on a single qubit only, right? That's why I'm mentioning it as a single qubit gate. For any general single qubit gate, we have this matrix A, B, C, D. When it operates on state 1, sorry, state 0, it gives me AC. And when it applies on state 1, so that is 0, we get BD. And you can see that this first column is the output when it operates on 0, and the second column is the output when it operates on 1, right? Second column, this is first column. Yeah, okay. So we have the structure of X gate here. Similarly, we can write the structure of Hadamard gate and Z gate. So you can see that it's easy to show that the structure of Hadamard gate will become 1 by root 2, 1, 1, 1, minus 1, this. And the structure of G gate will be, it does nothing when it applies to state 0. So the first column should be state 0, and the second column should be state minus 1. And minus 1 will be this. Okay. If we go with the same logic, then a gate that does nothing to state 0, but changes the state 1 to e to the power I theta 1 would look something like this. So with the same logic, if we want to construct a gate, we construct a gate. Let's say this gate is, what do I say? Let's say this gate is just m of theta. Okay, let me just call it p of theta, so that such that when p applies to 0, it does nothing, and when p applies to 1, it gives us e to the power I theta 1. So I can write this gate p of theta as does nothing to the first column, so the first column stay as qubit 0, and the second column becomes state 1 with e power I theta multiplied to it, so that would be 0 times e to the power I theta. Okay, and this is the general phase gate. Phase gate that applies a phase of theta to state 1, but does nothing to 0. And it can have special cases. So for theta equals to pi, we have already seen that p becomes z. We get the z gate. For theta equals to pi by 2, we get S gate. Okay, we'll have a look at this in a moment. And for theta equals to pi by 4, we get this p becomes something called T gate. And accordingly, the action would be the following. So when z applies to, we have already seen the action of z applies to 0, 0, and z applies to 1 is 1. For S gate, S applies to 0, S applies to 0. Okay, let's see. Maybe just write it first here, and then we'll look in the computer. Sorry about this. So S applies to 0 should give me 0, and S applies to 1 should give me e power I pi over 2. Oops, here it should be a 1. I'm really sorry. Because that was e power I pi, right? E power I pi by 2 times 1. Which is nothing but e power I pi by 2 was how much? We did it somewhere, right? E to the power I pi by 2. Where is it? Yeah. Theta equals to pi by 2, it gives a I. So this becomes I, right? So it becomes I times 1. And similarly, T0 should be 0. And T1 should be e to the power I pi by 4, 1. So pi by 4 equals to 1 by root 2. Right? How much it was? Pi by 4. Sorry for scrolling. For pi by 4, it is 1 by root 2, 1 plus I. The power I pi by 4, 1. So 1 by root 2, 1 plus I, 1. Let's check it. So we have already checked for Z. Now let's check for S and C. If S applied to 0 does nothing, and if S applied to 1 gives a phase of I, phase factor of I. So let's delete all this. Also delete this. So our state is in 0 nicely, and then we apply S gate. And we see that when S gate is applied to 0, nothing is happening. Now we want to apply S to state 1. I'm dragging it. Yeah. So S gate applied to 1 gives us a phase of pi by 2. You see? Yeah, pi by 2. And probability distribution of 1. I mean, it's the same 100%, but the phase becomes pi by 2, right? Yeah. Okay. What happens if we apply S gate twice? It should, let's see. S gate applied twice gives us a phase of pi. And that makes sense because pi by 2 and pi by 2. So it gives a phase of pi. Okay. Now let's see. Okay, this is a homework. I would leave to you what happens when you apply uh, T gate to 0 and 1. But I would just like to show that uh, if you apply T gate once, it gives a I'm not giving any homework. I'm just doing it for you. So if you apply T gate to state 1, it gives you a phase of pi by 4. You apply it once more, you give it a phase of pi by 2, right? When S is applied once, it gives you a phase of pi by 2. But for T, you have to apply it twice. And that's why you could say here that T square equals to S and S square equals to Z, right? Yeah, you can also just see it. And if you apply T gate to state 1, state 0, it is doing nothing. So we have proved all these single qubit gates now. Okay. Yeah, so I wrote it here, S square equals to Z and T square equals to S, right? All right. I have left another gate, that is the Y gate. That is another poly gate other than X and Z. And I hope you can check that out. Here is the Y gate. You could see how Y gate changes the qubits. All right, so we have looked at single qubit gates, the different single qubit gates. Next, let's go to multi-qubit gates.